Greetings, everybody. This is our first week of classes on video, and I will be as brief as possible to simply look at the subject matter that we covered last week. So, our first discussion was on the goals of the class, why ENE 446 is in our curriculum, and how it actually ties with ENE 244 and ENE 350 that most all of you must have taken by the time you've gotten to ENE 446. So this is really a course on computer architecture. It's called Digital Computer Design, and it deals with the issues of designing computers with performance in mind. And of course, when we talk about performance, we really have to look at a list of things that would come to mind. And these things would include things such as what makes today's computers so powerful and yet limited, what makes them heat up, use too much power, what makes them fast and what makes them slow, what makes them crave for more memory, what role does software and algorithm design play in computer architecture, what are the key metrics of computer performance, and those things are tied with our interest in using computers to carry out complex and time-consuming computations fast and efficiently very often. The speed of a computer may be impacted by a number of factors, such as the clock rate of its CPU, central processor unit, the amount of memory available for a computation, and the effectiveness of algorithms devised to run on it. Time and space are often tradable. That means we could have more space for less time, or vice versa. An example would be a table or a lookup table with n square locations to perform multiplication, rather than using a hardware or a multiplier circuit that would typically take longer to compute a product under the assumption that our memory is relatively fast. So this brings us to the notion of hard problems, in that even though computers do a lot of menial and a lot of laborious work in our daily interactions with them, there are some problems that are worth talking about here just briefly, that would make us realize that computers, as powerful as they may be, have limitations. It's really important to know these limitations before we leap forward and look at the brighter side of what computers can handle for us. Because without such a realization, we might be sort of feeling very good when we probably shouldn't be, because there are such problems that we may have to deal with from time to time. So in brief, these complex problems drain computers. And computer scientists and mathematicians identified numerous decision, search, and optimization problems that are known to take exponential time to solve. And here's an example of such a problem, which is called the subset sum problem. We talked about satisfiability in class, so I offer here a different problem, which is in the sort of same class of problems. So given a set of integers, these could be positive or negative, does it have a subset whose elements sum to 0? So you're now talking about the subsets of a set. And when we think about this, excluding the empty set, which will have no element in it, so there's no reason for us to be concerned to see if it actually adds up to 0 or its elements do. We are left with 2 to the n minus 1 non-empty subsets of a set of n integers, and a non-deterministic machine can potentially tell us what these sets are all at once. But we still have to go out and check if in fact the sum of the elements in every one of these subsets is equal to 0. Now this we could do in polynomial time because we have subsets whose sizes or cardinalities would not exceed n because we have a set of n elements to begin with. So we're, in the worst case, we're adding n elements, and therefore, and under the assumption that addition can be done in polynomial time, which we know it can be, and you'll learn that in ENEE446, we know that we could actually decide this question of a given subset of elements adding to 0 in a polynomial amount of time. That is polynomial in this number n, which is the size of our problem here. So this, of course, is if we were to have all these 2 to the n minus 1 non-empty subsets generated, and then we could run these all in parallel. So technically speaking, we could actually simulate a non-deterministic machine using a parallel computer with 2 to the n minus 1 processors. Each processor will simply work on the decision question, that is to say, if in fact the subset of elements that it is assigned to happens to add up to 0, and that's all it's going to decide. And every one of those processors, 2 to the n minus 1 of them, will decide on its own that same decision. Of course, this is not practical because we're now using 2 to the n minus 1 processors, which is exponential in the size of the problem n that we have. A deterministic machine, such as a sequential processor that you learned in 350, will have to test each subset one at a time, and then it'll take 2 to the n minus 1 steps to complete the search. So however you slice this problem, it looks like either we're going to use too many processors or too much time. And this cannot be worked around or cannot be handled with the machines of today as n gets large. Now people are researching other means of computation or the models of computation, and one of those is a quantum computer. And the promise it holds is that indeed a non-deterministic engine can be just mapped out to or mapped onto a quantum computer. That a quantum computer is this ideal non-deterministic machine which can do a lot of things in parallel and without requiring the number of processors that a parallel computer would require because of the principles of quantum mechanics, and I'll not get into those in this particular discussion here. So if we could sort of like summarize things real quickly, computer scientists kind of looked at these problems and then decided to or determined that these problems can be divided into about 4 classes roughly. There are other classes, subclasses that can be described along the way, but these are the most major ones. The class B of problems are those things that we could solve on a deterministic machine in polynomial time, sorting, searching, arithmetic computations such as addition, multiplication, division, whose solutions can actually be found in polynomial time. Those are class P problems. Class NP problems are those that are actually polynomial time in terms of execution, but the machines that they run on are not deterministic. They are on an undeterministic machine, and that they still take the subset sum we just looked at is one example. And a problem class, another problem class, is called NP complete. And this is the kind of problems or the class of problems where you have problems to which any other NP problem can be reduced by a polynomial time algorithm. In other words, you can set up the equivalence between a problem in NP and an NP complete problem by way of a polynomial time algorithm reduction. And satisfiability and graph-clique problems are examples. A graph-clique problem is a maximum clique problem is, for example, in a graph is to find the maximum complete graph, meaning that a graph in which a vertex, any two vertices are connected by an edge. So then there is the class of NP hard problems. Now these are the kinds of problems uh, that are known to be at least as hard as any other NP problem, and these do not necessarily have a polynomial time checking property either. I guess by way of an example, we could say subset sum of a clique problem is an example. And so if you take a label graph and then try to determine a clique, a maximum clique maybe, whose edges have labels that sum up to 0, even if you could have a deterministic or non-deterministic machine that could tell you what these cliques are in polynomial time, as we actually mentioned over here, in this class, you will still have to have another layer of exponential effort to decide whether in fact the clique you found has edges whose labels sum up to 0. So this is like a double whammy in a way. You have exponentiality in determining the clique itself in the search space, on top of which you also have exponentiality in time that will have to be put to use to determine if the label clique that you determine to be maximum actually has its labels sum up to 0. So that's a kind of NP-hard problem you can think about. Now we talked about this computational interactability in class on, I guess, Wednesday. And then on Monday we had begun to talk about, but Wednesday we kind of concluded it. So the example was that we had a pharmaceutical company that wants to market some new drugs, but before that could happen, that company would like to test to see if any two of these drugs taken together would cause a problem on patients. So what the company would do, that would try out as many pairs as possible out of the m times m minus 1 over 2 choices of pairs. And to do that, it will set up a beta test on our patients, each having or his own limit on the quantity of drugs that can be administered on that patient. So we denote these limits by AI for the M drugs we have. I guess this must be not M but an R, so I just made a mistake there. Let me just fix this real quick. That's the number of patients we have. And suppose that the reaction of the R patients to the M drugs are specified by an R by M binary matrix, where a 1 in the ith row in the jth column indicates a reaction and a 0 in the same position indicates no reaction to drug I, DI by patient PJ. Again, I think there's just a mess up there. Let me see if I could just change this drug DJ by patient PI. Because we just listed the rows as our patients. And then we assume that each patient is limited to have K drugs in a beta test, in each beta test. Even though that a patient may be able to deal with AI drugs, patient AI that is, at any point in time it can only handle K drugs at a time. So what the pharmaceutical company would like to do is to find out an optimum assignment of these M drugs to the R patients, in that it would want to maximize the number of pairs of drugs whose pairwise potency can be tested by the R patients. Okay, so I think we explained this in class, so I don't want to debate this any further. But the search space for the parameters we specified would be the AI choose K multiplied from 1 to R. That is A1 choose K times A2 choose K times all the way up to AR choose K. So just to put some numbers on this quantity, we choose M to be 20 as we did in class and K to be 5. And we set all of AIs to 10. And that's from 1 to 20. And then we, considering that we have 20 drugs, they will give us 190 pairs to compare, to check. And then also considering that each patient has a capacity of K, that will give 10 pairs from each, or by each patient at the maximum. And so we need about 20 patients. That will make it 200 pairs, and we'll then surpass 190 pairs. Thus we have, I guess this blocks it, so let me just move this over here. Thus we have such a large number of combinations that we have to deal with. I just simply plug these parameters in, and the quantity, as we did in class, of combinations we have to check comes to this. So then what we want to do is to see how quickly we can get this computation completed, and then we say that we have a super fast computer that can compute the number of pairs for each combination we check in about a nanosecond. This is overly optimistic, as we debated in class, because just to compare if in fact just to compute rather this particular sort of like set of pairs at each step for one of these choices of assignments we make to the of the drugs of the patients. So this is way too little time, I should say, to be able to do this. But even if we make that smaller, we would not be able to deal with this sort of computation, a number of computation steps, as we'll just see on the next slide. So the thing takes too much time. You know, we did all the algebra, and I did it a little more precisely here in this set of slides here. And it comes to 7.6 times 10 to the 23 years. And as I said in class, as you would all know, this is much longer than the age of our universe, which is about 14.5 billion years. That is 10 to the 9 times 14.5. So even if we picked ourselves a faster computer, like a picosecond, which is 10 to the minus 12 seconds per tick, we would only be able to reduce the time to about 7.6 times 10 to the 20 years. And you have to keep in mind that we're talking about 20 drugs in 20 patients, of very, very small numbers of patients and drugs. And even then, we get into this mess. So this hopefully demonstrates that our computers, however fast they may be, by the way, we could make this parallel also. We could make it, for example, to bring this to the age of the universe in terms of time, we need to use about 10 to the 10, you know, that is about 10 billion computers or processing elements, if you like. And that may be possible at some point in time. That may be to bring this time to the age of the universe. In other words, even if we had 10 billion computers all operating at picosecond speed, we would need to have about the universe, the age of the universe period of time, let's say, to be able to conclude this computation, just for 20 drugs and 20 patients. So this clearly is not the kind of direction we should go, and we know that we cannot make our computers faster to catch up with this, or we cannot replicate the quantity of processors. So we got to do something else, and then it ought to be to look for better algorithms, and that's what computer scientists have been working on. So these problems are generally known as branch and bound and backtracking techniques, and these are greedy methods. Essentially what they do is they look at the search space as a tree, as a huge tree, and they try to prune the tree. Of course, to be able to prune the tree, we need to have solutions that we expect to be relatively good with respect to our objective functions. In this case, we want to maximize the number of pairs. So the process typically proceeds in 2 steps. We do a depth first search on this tree randomly at times, and sometimes not so randomly, to determine, and the randomization would probably help us do this, to find a fairly large number of pairs in this particular uh, instance of the problem we're looking at. Once we get that number, then we could prune the tree by checking to see if at any point in the tree, as we go from the root of the tree down towards its leaves, we get to a point where traversing the path down from that vertex or node down would no longer give us anything better than what we have. So the depth first search is to find that good solution quickly, and you can sort of like dip down to the leaves from the root, maybe depending upon the size of the problem, a few, maybe a few thousand times. And then once you find a good number, you can then begin to dig, on a breadth first search basis, deeper into the tree. And if you ever actually find something bigger, as you have to go down to the leaf once in a while, then you can replace what you found. And so it sort of like progressively gets better, and then while also pruning the leaves of the tree. So we kind of describe these steps with an example in class, but I'm going to give you one more example here. And I just picked this four patient and 8 drugs example. And to simplify my representation, I had used a huge tree diagram. So what I do here, I write down my choices of traversals or assignments for each of these patients. So for the first patient, we have the first 5 drugs, and I've written down here the 5, and I'm actually limiting my K to 4. So 5 choose 4 is equal to 5, and these are the 5 choices of 4 drugs I can actually administer on the first patient. And the second patient will then have the last 5 drugs, so I'm going to take 4 out of those 5, and this particular list makes that set of choices. And then the third one will be administering, would potentially get up to 5 of these 3 to 7 drugs, and then I administer 4 of those, and these are the choices I could have. And then the last one could have 4 of the 5 that are actually marked here, and these are the ones that I have listed here. So we could see that we got 8 drugs, and so 8 choose 2 is equal to 28. And but we also have 4 patients. Each can do 6 pairs at the most, and that's 24. That's not quite enough to cover all 28. But we want still to maximize the number of pairs. And what I've done here, I've actually identified by way of these red patterns, tuples, quadruples, the choices that would lead to 21 distinct pairs. If you just do the, the operation by writing down these into pairs, you could see how that would happen. Roughly speaking, you can see that 4 and 5 will actually be overlapping here, and then here you would have 3 more overlaps with this. Let's see if I actually did copy this the right way. I might not have changed that the proper way. Let me see, 1, 2, 3, 4. So P1 needs to be updated here. P1 must be P1, 2, 3, 4. Just make that change real quick. So with this, these two have nothing in common. 3, 4, 5, 6 has 1 in common with P1, 1 in common with P2. That's for 5. Those two go away. We subtract from 24, so we're down to 22. And P4 has 1 and 2 in common, and nothing in common with this, and nothing in common with P3. So that's 21 distinct pairs is what we can get. Now, once we identify this, then we could actually see that we could avoid traversing the pads once we get to this P3 for several cases. And I just had given an example. Example is assigning quadruples in the first row to the first tree, like this, this, and this, like those three. You could see that you will have you will end up basically using having a running total of 14 pairs to really, you'll end up covering with these three. And of course, given that only 6 is left, you don't have to explore any one of these. So once again, if you look at these three together, given that we already found a 21 distinct pair combination by way of choosing the red ones, if you just choose this one, that one, and this one, and this one, not that one yet, actually just the first three, you could see that the 4, 5, 6 here overlapping with 4, 5, 6 over there, they will give you 3 overlaps right there. Out of the 18 that you're going to be able to get, you're now down to 15. And then you could also search one more. I believe you can find, let's see, what has the 3 and 4 here, and 3 and 4 are common, so they get knocked out. So you have 14 pairs at the most when you actually get down to here. So 14 plus 6, what is left over here, the most you can get out of these choices you will have, that is 4 choose 2, will not be large enough to offset or to go over the 21 you have. So once you get to this point, you can avoid dealing with these. And so I think you can check the other ones the same way. This is what the pruning is all about. Okay, so here's the first assignment that I'm going to ask you to work on. So it's kind of a similar problem. We have an online clothing store that would like to determine if its customers return one of the 18 designer shirts it sells when they buy 2 or more of them. And so we want to determine the minimum number of buyers needed to test all pairs of shirts to see if the purchase of a particular pairs of shirts lead to more returns, assuming that each buyer can buy up to t-shirts, up to 9 t-shirts, 9 shirts rather. And then in part B of the problem, if the store would like to run a market test to determine which pairs of shirts cause returns, how should it distribute the shirts among as few buyers as possible if this were to be some kind of a marketing ploy, so that all pairs of shirts are tested out at least once? So just to wrap it up, maybe you may have questions about this problem. You have 18 designer shirts a company sells, and company is interested in knowing if a buyer buys 2 of those shirts. It could be more than 2, but among the ones that he buys, some 2 shirts may make him make him return one of the shirts. This is what the company is wondering, if that's going to happen with certain shirts. It could be because of the style, the design similarity, the colors, etc. So what we want to know in the first part of the problem is to determine the minimum number of buyers that will be needed to test all pairs of shirts to see if the purchase of particular pairs of shirts lead to more returns. So we could run this experiment repetitively, or we could do it once, and if a patient happens to, not a patient but a buyer in this case, my mind went back to the pharmaceutical example, then we know that that particular pair is not going to be very successful. And we also know that each buyer can buy up to 9 shirts. So if the store would like to, in the second part, to run a market test to determine which pairs of shirts cause returns, how should the company distribute the shirts among as few buyers as possible, so that all pairs of shirts are tested out at least once? So in this second part of the problem, you're asked to actually design an assignment that will just identify. You have to give the shirts some labels, like label shirt 1, shirt 2, shirt 18, and then you have the buyers. So you have determine apparently in part A, the minimum quantity of number of, and then what number that is you will know, and then you'll just make the rows by that number of buyers. Now you're going to enter the ones and zeros, where the ones will say that buyer will try that shirt, will actually acquire it. Zero will say not. And then now you have to actually create the ones and zeros, and then you could see, you can convince yourself that that assignment that you created will give all the pairs of shirts for the company to test out. Problem two is sort of like a variation of the same, more like the one that we did in class. So if given an assignment matrix with R rows and M columns as described in class, design an algorithm to obtain an assignment of M shirts to R buyers that maximize the number of pairs of shirts tested on the buyers, assuming again that each buyer can purchase up to K shirts without running over his budget. And then it asks you to test the algorithm that you develop, by writing an actual program in a language of your own choice. It can be Mathematica, C, C++, Java. You pick it. The numbers are given as R equals M, and that is equal to 18, and K is equal to 5 here. And the matrix that you have to deal with, which is coming on the next slide. And then the question says, what is the complexity of your algorithm? We can actually write the average complexity, worst time complexity, best, and then compare it with the time that your program seems to be taking. And here's the matrix. So this is actually in image form, maybe some bitmap or a PIC format, and so I will email you along with this assignment a text version of it, so you can actually you don't have to recreate this matrix when you do the problem. So let's just say that we've covered as briefly as I said I would. Probably have taken too long. What we did in first week, and this week we're going to switch gears and look at performance in a different way, by thinking that we have work engines. So we'll introduce the notion of work, throughput, speed up, efficiency, utilization, and redundancy. All those concepts will be covered beginning this week and running into the end of the next week. So I'll see you in class later today. Until then, take care.